Welcome back, AP Bio. This is our last Nearpod lesson of the week. And in this lesson, we're going to learn about the chi-square test of independence. So we have been using the chi-square test before. We used it in our last unit when we looked at the effect of leptin on the amount of cells in mitosis. We are coming back to chi-square. It never goes away. We're going to now use it to test to see whether genes are independent of one another, meaning that they are unlinked. So when you do this chi-square test of independence in AP Stats, they're going to call it the chi-square test for association, but bio needs to be special, so we call it the chi-square test of independence. So let's do a quick review of what a linked or unlinked gene is, and I have some images there for you to look at. And notice on these images that gene A and gene B are linked. They are linked because they are on the same chromosome. And because they are on the same chromosome, they are more likely to be inherited together. So those traits normally are associated with one another. However, that is going to be different from gene A and gene C, and those are on different chromosomes. So those traits are inherited independently, and that's what we're going to test today, whether or not we have traits that are inherited independent of one another. So what we're really looking at is to see if genes are linked or unlinked. So some things that are going to stay the same with our chi-square analysis. We are still always testing our null hypothesis, and our null hypothesis is that there is no effect. So for us, that means that there is no correlation between the inheritance of genes. That's our null hypothesis that we are going to be testing. That means that we're testing the hypothesis that two genes are inherited independently of one another, meaning that they are unlinked on different chromosomes or very far apart on the same chromosome. Because remember, even if genes are on the same chromosome, if they are very, very, very far apart, there could be crossing over that occurs. And look at all of that distance in between these two genes. If you have genes that are very far apart, it's more likely that crossing over effects could happen and that those genes could be inherited independent of one another. So let's do a quick review of the chi-square equation. It is right here. Notice that chi-square is going to be equal to the summation of the observed minus expected squared divided by expected. You're going to use that equation along with this chi-square table. This chi-square table will use the p-value. We're always going to use a p-value of 0.05 and then our degrees of freedom to find critical values. And I'm going to outline all of these critical values in red, and this is what we're going to compare our chi-square value to, and that's going to allow us to make the conclusion on whether or not these genes are correlated or not. So now that we have reviewed the chi-square equation as well as the critical value table, we're ready to look at our first question of the day, and that first question is, are the genes for red hair color and freckles independent? Meaning, are they on different chromosomes and are they inherited independently of one another? So remember that when we're doing our chi-square test, we are always looking at the null hypothesis. So our null hypothesis is our no effect hypothesis. So that would mean that the genes are not correlated, meaning they are inherited independently. And I am a horrible speller, but spell check always saves the day. So that is the null hypothesis that we are testing, that the genes are not correlated. They are not inherited together. So let's look at the data that we have from this genetic test. And we are looking at an F1 test cross. Remember that an F1 is always going to be something that is completely heterozygous. So we're looking at two different traits. So we're going to assume that those are on two different genes. So this would be our F1. And then our test cross means that we are going to do the genetic cross with something that is completely homozygous recessive. So that's the cross that we expect to see. Our expected ratio for this F1 test cross is a 1:1:1:1:1 ratio. So what we would expect is 1/4 would have red hair, no freckles, 1/4 would have brown hairs and freckles, 1/4 brown hair, no freckles, and 1/4 red hair and freckles. But if you look at our observed values, that is not what we see. Instead, we see a vast majority that look like the parental phenotypes, that look like the F1 as well as the homozygous recessive. So these are parental phenotypes. The other thing that we see is a smaller amount of phenotypes that are recombinants. So before, when we looked at this type of F1 test cross, we used these observed values, and we assumed because these parental phenotypes were so large that these genes were actually linked, that these things were inherited together, and we used the recombinant frequency to determine the distance between these two genes in the chromosome. What we are doing today is we are going to use the chi-square test of independence to do a statistical test to support the fact that this null hypothesis is disproved, meaning that these genes are going to be correlated and that they are actually inherited together, and we're going to reject this null. So we're going to calculate the chi-square for independence of the two traits in our table 1 above, and then based on our results, we are going to see if the traits for red hair and freckles are actually independent of each other or not. And then we have to use this mathematical equation to justify our conclusion. So here's a table of our chi-square data so far. I have put in the 4 different phenotypes as well as the observed values. The next thing that we have to do is we have to determine our expected values. And we already know that we would have expected a ratio of 1:1:1:1 if the genes are unlinked, meaning that they are inherited independent of one another. That's what we would expect. But I don't see equal amounts of these genes. So we're going to do the chi-square to actually reject the null and disprove it. But the first thing I'm going to do is I'm going to take 12 plus 18 plus 431 plus 439. I'm going to add all of those together, and I have a total progeny of 900. Now that's going to be important because that's going to help me determine my expected value. Because if I have a total of 900 progeny and I multiply that by 1/4, because that's what I would expect, I'm going to get 225. Because a 1:1:1:1 ratio means I have 1/4 to 1/4 to 1/4 to 1/4. So my expected values for each of these phenotypes is going to be 225. And that's how I determine those expecteds. When I continue with this chi-square, this is observed minus expected squared. I forgot to put in that superscript right there. So I'm going to take 12 minus 225, square it, and then divide by my expected. So let me write that in just in case we've forgotten how to do that math. We have to subtract, square it, and then divide by my expected. When I do this for red hair and no freckles, I get an answer of 201.64. I'm going to continue this same mathematic equation, and for the next row I'm going to get 190.44. For the third row, 188.60. And then finally for red hair and freckles, when I do the math, I get 203.54. So that's just my observed minus expected square divided by expected. To find my chi-square value though, my chi-square value is the summation of all of these numbers. So I need to add 201.64, 190, 188, 203, and when I add all of those four values together, I get a chi-square value of, I believe, 784, if I did my math correct. So it is a huge, huge chi-square value, but that is not enough. That's not enough for me to make my conclusion because I have to compare it to a critical value. So notice here that I have 4 different phenotypes. When I come all the way up to my chi-square table, I'm going to look always at a p-value of 0.05. That's a 95% confidence level. And when I determine my degrees of freedom, that's going to be equal to the number of distinct possible outcomes minus 1. So I had 4 different phenotypes, so my degrees of freedom is 3. So I know that the critical value I'm going to compare it to is 7.81. So my chi-square value is much greater than 7.81. And it is that comparison that I'm looking at. Now, a small chi-square value, a value that is smaller than my critical value, supports the null hypothesis. This is much, much greater than my critical value, so my null hypothesis is rejected. That is my conclusion. However, I need evidence to support that conclusion, and my chi-square value of 784 is larger than the critical value of 781 determined by a p-value of 0.05 and degrees of freedom of 3. So notice that it is not enough for me just to put what my conclusion is, that the null hypothesis is rejected. I need to support that conclusion with mathematical reasoning. So you always have to compare your chi-square value to that critical value. If it is smaller than that critical value, it supports the null. If it is larger, then we reject it.